Hello, my name is Samantha Cope, and today I'll be sharing the results of a collaborative project integrating traditional vessel tracking tools for an initial assessment of underwater noise in San Francisco Bay. This project was part of my graduate research at San Francisco State University with Ellen Hines, Roger Bland, and Jerry Davis, but also would not have been possible without my colleagues at Protected Seas, Brendan Tugger and Virgil Zetterland. San Francisco Bay is highly urbanized with a wide range of vessel use, including commercial shipping, substantial ferry service, and recreational traffic. Harbor porpoise and bottlenose dolphins are present in the bay, and in recent years, larger whale species have been spotted more frequently in bay waters. Here, you see a recent interaction between an oil tanker and a humpback under the Golden Gate Bridge, and below, a gray whale surfacing near a high-speed ferry during the unusual mortality event beginning in 2019. Since that time, there has been an alarming number of gray whale carcasses washing ashore in the Bay Area, some with evidence of collision. Compared to other places along the U.S. West Coast, the Bay is relatively understudied, and with these species present, it's imperative that we document and evaluate human impacts. So how do we do that? The Automatic Identification System, or AIS, has traditionally been used to inform analysis of larger vessel traffic. But in an urban area, where small vessels aren't required to use AIS, it can leave parts of the full picture missing. Previously, we found that at least 1/3 of all traffic here was not broadcasting AIS. The Protected Seas Marine Monitor, or M2, is a solution for filling these data gaps. It's a monitoring platform that uses marine radar paired with a camera to track all vessels, regardless of whether or not they participate in other tracking systems like AIS. The camera is autonomously directed to vessel positions to capture photos so that vessels and their activity can be identified. The M2 platform takes data from all these tools, including AIS, and seamlessly integrates them in an online data viewer. Here, you can see a ferry tracked by radar, photographed, and linked to its vessel name in AIS data. M2 was originally conceived as a solution for monitoring fishing activity in marine protected areas, or MPAs. And earlier this year, M2 data from Southern California was used to prosecute illegal fishing. Here, you can see the radar imagery where it's clear the vessel was lingering in the MPA, and the photos helped confirm the activity. Currently, there are 19 M2 sites worldwide. Most international sites are focused on monitoring artisanal and commercial fishing, like in Indonesia and Ecuador, and these fishing practices can have impacts on local species. Monitoring in marine mammal habitat is a primary concern at some of our sites, including San Juan Island, Washington, in killer whale habitat, and near San Francisco Bay. Next, we'll zoom into the area I'll be addressing today in the Central Bay, shown in blue. As you can see in the radar imagery, solid objects, like land, limit the radar's range. The gray track line shows the path of that ferry that was broadcasting AIS data. M2 collects data 24/7, and we used 11 days of data from early 2018 in this study. The specific questions we sought to address were, what vessels are in the area? How fast do they travel? And what is their noise contribution to the underwater soundscape? We collected vessel data using the M2 system located at the Estuary and Ocean Science Center of San Francisco State. We collected acoustic data from a hydrophone deployed off the center's research pier, using 2 frequency bands to generally observe sound relevant to the larger and smaller cetacean species, and within the limits of the existing hydrophone. This image shows a vessel passage by the center. At the closest point of approach, we calculated the received level at the hydrophone in 1/3 octave bands. Since energy is lost as sound radiates from a vessel, we modeled transmission loss to estimate vessel source levels. To calculate that loss, we used parabolic equation modeling with local bathymetry and water quality to estimate an appropriate general loss model. Then, we estimated a vessel's source level in each frequency band. Once we had estimated source level, we used the same loss model to estimate received levels across the study area. This example shows the modeled levels within the lower frequency band from a single point in time along a ferry's track. To show the accumulation of sound energy over time, we calculated sound exposure level across the study area every 60 seconds. This image shows the cumulative exposure as the ferry passed through. We determined the cumulative exposure over each 24-hour day as a result of each vessel type and averaged these daily maps. These vessel types were most common in the area. I want to note a high presence of sailboats and tugs that are not included here due to difficulty isolating these vessels acoustically. Ferries were overwhelmingly the most common, traveling at an average speed of 33 knots. One note on recreational craft. Our previous research showed variation in their activity throughout the year, so results presented here should be interpreted as specific to winter in the area. For tankers and bulk and vehicle carriers, it's important to note they commonly traveled at or above 10 knots, especially vehicle carriers. 10 knots is frequently used as a speed limit to mitigate deadly vessel strikes. As expected, most of the larger ships were associated with the highest source levels. When we're thinking about how loud vessels sound to cetaceans underwater, there are a lot of variables to consider. But as we learn more about how they react to vessels, it will be important to think about how much time they might have to avoid collision with a fast-moving boat, like a ferry, once they might detect it. Shown here are the daily sound exposure levels. It's not surprising to see that ferries contributed the highest levels, given their constant presence. What's interesting regarding recreational craft is that even though they were generally the quietest vessel type, the way they used the area is likely more varied, and thus their sound contribution has a larger spatial footprint here. Even though commercial ships were less common than ferries and recreational craft, it's important to acknowledge their potential impact. The waterway is extremely narrow compared to the open ocean, and animals and ships can find themselves in very close proximity. Ferries have a pervasive presence, and routes are expanding. To our knowledge, we don't know of any evidence of a ferry colliding with a whale, but there have been close calls, like the photo I showed at the start of the presentation. Recreational traffic is dynamic and does often travel at higher speeds. I'm excited to share that M2 will expand to the U.S. East Coast this year, where it will be used to monitor vessel speeds in the seasonal management areas for critically endangered North Atlantic right whales. In California, M2 monitors traffic speeds where voluntary slowdown measures have recently been expanded. And in Washington State, M2 is also paired with the hydrophone to inform certain vessel sound characteristics. Beyond the U.S., one recent deployment to Malaysia hopes to link vessels with underwater sound of fish bombing in a sensitive marine ecosystem. And there has been interest in multiple locations in using M2 to match small-scale fishing activity with its sound signatures underwater. Ultimately, M2 is being used and considered around the world anywhere small-scale vessel activity is of interest. By repurposing traditional maritime tools, like radar, in a user-friendly platform, M2 provides both a novel and accessible research tool for all. More details on the methods used and further results can be found in our publication in the Journal of the Acoustical Society of America. You can reach me and my team at m2@protectedseas.net. I want to give a special thank you to M2 partners in the Bay Area, San Francisco State University, and the Marine Mammal Center. And thank you all for taking the time to listen today.